Hi everyone. In the previous lecture on microelectronic circuits, we were discussing about how to find loop gain for a negative feedback circuit. What we said was that loop gain in itself, whatever be the amplifier topology, current, current input, current output, voltage output, voltage input, current output, or current input, voltage output. In all the four different amplifier topologies, we said that loop gain is a dimensionless quantity. So to find loop gain, you have to just break the loop at some point, apply a voltage, and then return back to the same point. So if you break a loop at some point and then return back, traverse the entire loop, and return back to the same point. By doing so, we can estimate the loop gain. And we said that loop gain is extremely important because it determines everything that you need to know about a negative feedback system. That information is fully captured in the loop gain. We'll know how impedances change, we'll know how gains change. We will also be able to say the system is stable or not. We haven't yet properly come to discussing about stability in feedback systems. So that's a separate topic in itself. Okay, so we'll spend a good deal of time about the stability of feedback systems. But right now, I'll just finish off our discussion on the negative, rather finding the loop gain in negative feedback systems. So what we said was that find out one node where the looking in input impedance is infinity and just break open that node and apply a test voltage. This is what we said. Find out some node where the input impedance is infinity. So that's the current drawn inside is zero. Break the loop at that point and then apply a test voltage delta V and traverse and return back to this point. So that's what we said. And we also took some examples and saw how to calculate the loop gains. But now let's assume that there is no such node in the circuit where the input impedance is infinity. You are not able to find any node in the circuit where the input impedance is infinity. Now that we have understood circuits to a good level, we should be able to see that if you want to find loop gain in a circuit where there is no node where the input impedance is infinity, then what you do is that you can pick any node and then let Z2 of S be the input impedance looking into this node. Then what you do is break the loop and then load the first stage with the input impedance of the point where you broke the loop. So what you're doing is now if you see the circuit, as far as the first amplifier is concerned, I've shown a cascade of two amplifiers A1 and A2. As far as the first amplifier is concerned, the second amplifier is entirely just going to look like an impedance of value Z of S, Z2 of S. So therefore, when I'm breaking the loop, I'm ensuring that the conditions remain the same, before breaking the loop. The same conditions hold true, or rather the amplifier A1 is going to see a similar output before we broke the loop. So that's what we should do. Just load this amplifier with an impedance of Z2 of S. And then we can perform the analysis, we'll get the same answers. So in this case, find the gain individually for these two stages and you can multiply the gains of both the amplifiers. Okay, that will give you the overall gain of the cascade of two amplifiers. So this is what we are going to apply here to find the loop gain for negative feedback circuits. So this is a circuit which we have already analyzed in the previous lecture. I think lecture 77 or 78. You can go through that. Where we broke the loop at this point. We broke the loop at this point because we saw the input impedance here is infinity. And then we found the loop gain. But now I'll try to analyze the same circuit and we will get exactly the same result if you break the loop at any other point as well. Now let's break the loop at this point. I'm going to break the loop at this point. If I break the loop at this point, what should I do? What is the looking in impedance seen in this node? What is the look? I'm looking into this node, so you have RF and 1 by GM1. So it will be RF plus 1 by GM1. That's the looking in impedance at that node. So what you have to do is that you'll have to load this node with an impedance of Rin, where Rin is given by RF plus 1 by GM1. And then analyze the circuit. So I've applied a voltage delta V at this point. So delta V, the voltage coming at this node, the looking in impedance here is 1 by GM1. We are neglecting R0 here. So the voltage at this node here is going to be 1 by 1 plus GM1 RF. So then multiplied by GM1 into R1. So this multiplied by GM1 into R1 will be the voltage at this node. Multiplied by GM2. So this is a common source, PMOS common source amplifier. So this whole term here, multiplied by the gain of the second stage, so which will be minus of GM2 into R2 parallel RF plus 1 by GM. So this is going to be your expression for the loop gain of this amplifier. Okay, so that's what we get. And if you assume RF to be much greater than 1, if you assume RF to be much greater than 1, then of course you can easily show that the result, so I can ignore 1 here, GM1 and GM1 will cancel out. This result will this term can be ignored because RF is much larger compared to R2 as well. I haven't explicitly said that, so let's assume RF is much greater than R2. We will get the same expression which we derived in the previous lecture. So it is GM 2 R1 by RF. So this is going to be your loop gain. So you can go back and look at the previous expression we derived in the previous lecture as well. You'll get an exactly same expression for the loop gain. Okay, so you can verify this, apply the procedure anywhere at any node. You'll have to ensure this impedance loading condition is done properly, met properly. I'll take another circuit, which is the positively feedback circuit. So this is a circuit we analyzed in the previous lecture as well and found the loop gain. We chose to break the loop at this point. Since we broke the loop at this point, we were able to easily find the loop gain because the input impedance here was infinity. But now let's break the loop at this point here. If you break the loop at this point, what is the looking in impedance at this node? If you look into this node, the looking in impedance is R1 plus R2. So you'll have to load this node with R1 plus R2 and carry out the analysis. So apply delta V here and you'll be able to, again, see this is a very trivial thing to do, but for the sake of completion, I wanted to discuss this part as well. So apply delta V and at this node and come back to the voltage at this node, you get the loop gain. So if you apply delta V here, so you get the voltage at this node here is input should be grounded when we are finding loop gain. So at this node, the voltage is the gain is going to be R1 by R1 plus R2 multiplied by the gain of this stage, which is minus of GM RL, multiplied by the gain of this stage, which will be minus of GM into R1 plus R2. So you'll be left with minus of GM R1 into minus of GM RL. So that's the loop gain for the circuit, and this exactly matches with what we have calculated in the previous lecture as well. So that's it. So we saw how to analyze and find loop gain for negative feedback circuits. One important thing we said that was that in negative feedback circuits, since the loop gain is a dimensionless quantity, whatever be the circuit, voltage amplifier, current amplifier, transimpedance or transconductance amplifier, you can just break the loop at some point and apply an voltage and find the voltage at the same node after traversing back the entire loop, and the ratio of the two voltages will give you your loop gain. Okay, and we saw how to find it in two different methods. In the first case, we assumed a circuit where at least there is one node where the input impedance is infinity. In the second case, we saw that, okay, if there was no node where the input impedance is infinity, then how to find it? We said load the node where you are breaking the loop, load that node with the input impedance of the previous stage, okay, or the next stage, I'm sorry. So that's it. In the next lecture, I'll talk a little bit about some doubts and some very basics about feedback and stability in in simple positive and negative feedback systems.